It's a pleasure for me to present this case study of Marriott Hotel before you. It's always an experience standing over here on that stage, sharing the dais with such eminent people, listening to such lectures, getting information, because every lecture over here since morning, these 2 days, throughout the year, MXBM holds, they have different informations. You learn something new. So, thank you Avneet and team for having me over. It's always a pleasure being over here. I'd like to present one of our case studies or projects which are it's an ongoing project. It's the Marriott Hotel at Bhubaneshwar. This project is actually, so this project was actually envisaged with an RCC structure. This is totally RCC frame structure, and it happens to be Marriott's first structure in India made completely of steel. And I think it's the second 5-star hotel in India which is coming up with complete of steel. I think the first being the Shrem Group in Bombay, near the Bombay airport. So when the owner, which is Luxury Assets, they were into the projects, and almost 1/3 way into the projects when the RCC design was finalized, construction had started, there was a sudden time analysis which led to the feeling that they are going to exceed the project completion time by almost quite a bit of it. Now, that's when we were working as a proof consultant for that project, and that's when we were called in, and we were asked to do a cost analysis, time versus cost analysis for this thing versus an alternate material. And that's when the ball started rolling for this project being into a steel frame structure. So this is an architectural view, architect's perspective. The project, again, as I said, it's an ongoing project. It's still not completed. It's envisaged to be completed by 2025. So right now, it's an overview of what the project has been through, what are the softwares used, what are the detailings done, and what are the engineerings involved behind this project. So this was the original model of the RCC frame building, which of course, the framing structure is the same, except for that, just as a steel, what happens with the steel building is that you introduce a lot of bracings, you introduce a lot of connections, sizes change, the internal sizes, the road mappings, internal buildings change, the ducting systems change. Those definitely got changed, but the basic framework and the basic architecture remains the same. It's a double basement, ground, and 11-storied building with 10 stories and 1 terrace. So this is being developed on a 7,000 square meter land area in Bhubaneshwar, and it's in the heart of the city. And as I told you, it's a double basement, ground, and 11-storied structure. Again, envisioned as a RCC frame structure, designed as an RCC frame structure, and then got into a little bit of a time crisis, and that's where steel came in. We've done a couple of steel structures earlier, so that's when we sat with the cost analysis, and we found out that the time versus the ROI against this building, because this being a commercial hotel building, the ROI is, again, a lot to do with the time. Steel would be an appropriate material, but it's just not about just designing or just implementing this with steel, because a hotel structure or a structure where people are going to reside, they're going to stay overnight, and that needs a lot of calculations, a lot of vibration analysis, which has to ensure that the customer is safe, or the person who is visiting or staying in the hotel, they don't undergo any sort of difference than RCC, what they would have undergone in RCC structure. So that's one bit of an analysis part. Now, this again, once it was decided and the steel structure was decided on, and we then had to visualize along sitting with the architect that how could we actually change this into a steel structure without affecting the architecture. Why I said this that, see, when you architect a building using, having RCC in mind, then you are limiting your column spacing, you're limiting your beam spacing, you're limiting your beam span. So which then if we convert to steel, might turn out to be a little more expensive. And that's general with everything. If you already architect it as a steel structure, then you'll go in with a higher span. We'll go in with a higher span beams. You'll go in with a much more flexibility on the height of the building, because your RCC beam depth and the steel beam depth will definitely differ. So obviously, then again in the RCC steel beams, you can pass the ducts and the services through the beams. You can do that. It's difficult in RCC. It's not impossible, but it's difficult in RCC. So the height of the building changes or alters. So we have altered it, but to a certain extent. So this would be the actual model image. This is the model image of the final model of the steel structure. And there are, again, two basements. The basement has a retaining wall around it, just like in a regular basement. It has a base raft, but the internal columns and beams again start from steel, from the base raft itself. We did not go up to ground level with concrete and then go up. So we started the steel structure from the base raft itself. So these are some of the features which you have in, which you have, each of these floors have. So the lower basement has the parking, it has the STB rooms, it has the water tanks, it has the HVAC and other areas. Then it has, the upper basement also has the parking, it has the BOH area. And then when you go to the ground floor, it has the banquet. If you see, the residential part starts from the 5th floor, but before that, all the services, all the frills and frolics of the hotel start from the ground floor, banquet lobby, hotel lobby, all the dining, cafeteria, then a bar on the 1st floor, 3 banquet halls on the 2nd floor with a pre-function and a boardroom. That's what you generally use for a hotel. These are regular requirements of a hotel. And you have the gym, spa. The 4th floor is sort of a dummy floor. It exists, but it doesn't have any services on function. It's called a transfer or service floor. Why is it a transfer floor? Because it doesn't have the exact height required for a regular floor, but it has all the services lined up over there. Because over there, there is this building has a swimming pool deck and an open garden deck, which is again a 1.5-story height area. That's why we have an intermediate 4th floor, which is again a transfer floor, but not a regular floor. But again, after the 3rd floor, there's something called the 3rd floor mezzanine, which is partial, but which is not complete, but again, it has the capacity of holding people over there. Then on the 5th floor, it starts with the 17 guest room, and then 1 suite and 3 number of the boardroom, and then onwards, it's entirely residential until the 10th floor. And then you have the terrace, and then the roof, the upper terrace. The total number of rooms over here would be around 143, and suites around 6 with a presidential suite. So now, we'll just delve into a little bit of the data and the design which is there in the drawing. The architectural part of the whole building. So it has, the basement extends around 10.4 meter below. So you have 2 basements which extends totally of 10.4 meter below ground and approximately a 51.5 meter above ground superstructure. Which means in an area like Bhubaneshwar, you have to design such a high structure with super cyclone wind speed. Bhubaneshwar is actually subjected to high wind speed to a huge extent. As I mentioned, the 4th floor is the service floor. It also has a swimming pool outside. And here, this portion of the floor actually terminates, and then the residential portion is a separate portion. So I'll just show you once we see the architectural drawing. Again, the 5th floor, as I mentioned, is the residential area, and it has access to the swimming pool deck. And one of the biggest key features of this whole building is a floating banquet hall, which extends around 7.6 meters beyond, cantilevering 7.6 meters out. And then it is actually not cantilevering only out, it is actually supported by floating columns on the exterior. So as and when we go down the slide, we'll get to see how a floating column and a cantilever combines to hold the whole banquet. This is the elevation. I don't have a pointer, so I'll just try to show you by my. So this is the elevation of the whole building, and you can see there are cantilevering portions out with girders which has to extend to hold the cantilever and yet ensure that the deflection, because it's a banquet hall, there's movement, there's high commercial loadings, so you have to ensure, and at the same time, if there is any adverse catastrophic winds or earthquake forces, you'll have to ensure that then it does not, it sustains all the deflection criterias. So the structural thing, a part of this whole project is that it almost consumed 2,400 tons of steel. My personal take on this, we could have restricted it to 2,100 to 2,200, provided we had initially architected this as a steel structure building. But then again, once it's, you restrain yourself with RCC framing, then you'll need to adhere to that. So it's okay. I mean, it has actually saved a lot of time for the client, which is why we are happy. Because again, as I told you, the frame structure is based out of, the column layout is based out of RCC frame, so we are following the same design, same layout. Over here, another special feature of this project is we've used a metal deck, which is manufactured by a company called Vertical Performance Structures, based out of Bangalore. They are also the fabricators and erectors for this project. So they have their special metal deck, which allows, we have shear studs, we have composite action, but it allows the whole structure or the slab to behave as a composite slab, but also as a ribbed slab. And because it behaves as a ribbed slab, you don't need intermediate beams. In general, composite deck slabs can span between 2.5 to 2.8 meters or 3 meters for a 1 millimeter thick deck. Over here, we used a 0.8 millimeter deck with a span of at least 10 meters. The reason is the decks are deep deck. We have reinforcements in the deep deck portions. They act as ribbed beams and they support the slab. So that's one other interesting feature of this project. So the beam column joins over here, what we did is we don't have secondary beams much. It's like you have a room, you have the beams connecting to the columns, but we don't have majority, at least 90-95% portion, we don't have beams connecting to beams. So there are no secondary beams, there are all primary beams. Which is why now in a building system, what you do is that when you analyze a building, either you can make the entire building rigid and make sure that all the columns are lateral columns. When I say lateral columns, it means the columns and the beams will take earthquake, wind, dead, live, all vertical and lateral forces. And when I say gravity columns, it means it's just going to take in vertical loads. Now in this building, we had, though we have considered rigid joints in between beams and columns, because all the beams are framing into columns, and we tried to avoid bracings, but at the same time, not all the frames are lateral frames. There is a mixture of gravity frames and lateral frames. And the lateral frames are the ones which will take in load. We don't mind it being heavy because the way you plan out the lateral framing portions are where the architect allows you to introduce bracings and to enhance the column size. So you attract, excuse me. So when you build lateral frames, it means you attract, or the columns are allowed to attract all the lateral forces to within those frame areas, right? That saves other portion columns into lesser size, which means I'm just designing that for gravity. Excuse me. Okay, so another part which we have done over here is that to reduce the tonnage, instead of I sections and making it heavy and plated, there are some columns which are double web I sections. In a double web I sections, there's one problem, that you need stiffness in between the webs, but it reduces the plate thickness, but it increases the IXX of the column. So this was modeled in ETABS. The composite nature is a hand-driven calculation. because we use decks which are not regular in the library. So it's an ETAP-based software. The geometry is something similar. It's exactly like this. And of course, the member sections have been modified. It has been optimized. But this is the basic geometry. So of the entire building, these are the only RCC portions which we have used, except for the slabs, floor slabs, yes, with the decks. But these are free from the decks. The red wall you see is the retaining wall, which extends around 10.4 meter below ground. That's a retaining wall for the basement. Then you have the lift elevator core wall. We've used this because, you know, they act as a shear wall. They can actually reduce your other member sections of the thing, of the whole building. And then you have the water tanks, which actually has the RCC wall. Excuse me, can I have some water? Can I have some water? Sorry. Sorry. Okay, so again, as I mentioned, the RCC, so the base shaft is completely RCC, of course. Then, to initiate the steel columns, so we made around 600 to 700 high pedestals from the base shaft to accommodate your base plate. And then we started the column from there. And from the upper basement onwards, we have the steel beams and the columns. To the steel beams also frame into the RCC walls. But when they frame in over there, there's a bracket, but it does not transfer any lateral load because there is a expansion joint, or rather the slippable joint, a slotted connection over there. We wanted the retaining wall to behave like a retaining wall, but not from any transferring load from the building to the retaining wall. So over here you can see the main frame beams, or all the beams are framing into columns. And you have the columns over there, which is shown in circle. Let's just shown two of them. There are hardly any intermediate beams. So the entire floor or any of these beam, you can't see any intermediate beam, and it looks like a long span or a high span. Most of these are all plated with a plate of 350 grade steel, which is why we could economize on the thickness of the plate. And then even the beams are made from plated structures, so that we could actually defer the beam sections. We have actually made trapezoidal sections, we've made truss sections, but we've been able to economize on the tonnage, optimize on the tonnage based on the fabricated. This is how a double web column look like. It's simple, but it is very effective. And now, when you have 4 beams connecting to this column, the problem is not the beams connecting in the flange, but the problem is the beams connecting to the web. So you need stiffeners at the beam locations, and yet you need a through and through bolt. A stiffener with a through and through bolt serves a good purpose to hold the beams from both the ends. Now maybe the beams are not in 90 degree, it could also be at an angular section, but we took care of all of them and the stresses arising from them, passing through the bolts into the columns. But the columns over here, what you cannot see is the stiffness inside the double webs. So, though all the main frames are rigid connection and supposed to behave like a lateral, but there are core main frames with some bracings, without some bracings, which attract the main lateral loads. Mainly, guiding point is the wind. Though earthquake, there are some areas, some zones where the earthquake forces dominate. So it's a combination of both together. So we have the metal deck construction. This special type of metal deck has avoided any secondary frame, and the angular and the final arrangement of beams are in conjunction with the architectural layout. The sheetings and all, these are all the cladding materials. We have not, it's not nothing to do with much of the structure. So this is how a metal deck was looking like. These are all the metal decks which you can see, which has been stored on the floor. There's a partial casting. I have given a partial because so that to show you, we have an image later. So you can see there are the deep decks of the metal deck are actually behaving like rib beams with actually trapezoidal reinforcements induced in them. Okay? So once you have that, then because of those reinforcement and this behaving like a rib slab, you don't have intermediate beams connected. You don't need them. So this is the feature of the metal deck. This is how the rib slab looks like after casting. These are the reinforcements pattern of a rib slab, and these are all nominal reinforcement between maximum 12 dia. And the decking varies between 140 and 150 millimeter depth, and it's in 0.8 meter. And by the way, the decking which we do is generally an unpropped, because if you use a prop decking, you can actually economize on the decking and economize also on the slab. The difference between a propped and an unpropped decking is that when you use a prop decking, it means during the green concrete stage, the prop will take the deflection. And if you do an unpropped decking, it means during the plastic concrete stage, that is the green concrete, the decking and the beam has to take in the load even when the composite action has not started. Sorry. Okay, so these are some of the architectural layout and of the beam. Just one thing over here I wanted to show you. So this is the cantilevering portion out. So we have made truss girders, we can see in the lower part of the image, which actually project out and hold the column and the banquet hall, beyond which and it's resting on these floating columns. These are some of the Tekla detailing we did. Use the software called Tekla to detail out all the connections, which is very easy. And you can see in the coloring portions all the trusses which actually hold the banquet hall projected slab. This is one of these are the detailed drawing of the truss, and that's how the drawings are done for this thing. So just to give you how we have used a plate girder. So you have the truss girder holding these floating columns, and then you have the cantilever beams, and this area is empty. So it's a 7.6 meter cantilever holding the entire banquet. It's a double-story, double-height banquet. So entire load which has been taken is taken by it's transferred from the floating column to the truss girder into the mainframe buildings. These are some of the construction stage of this whole thing was done in three sequences. So there were like A, B, and C. A and C were constructed first, and then the B was done. This is because of to save time. These were the construction analysis was also done. Erection analysis was done. This is the construction image which is still going on. These are in the earlier stages in last year. And this is the final, this is the recent image of in February. It's still in progress. And once it's done, so we will have a Marriott Hotel completely with steel. Thank you so much.